It's great to be back here. I think my association with the lab goes back 30 some odd years at least. First as a working physicist with the nuclear physics folks here in computation and experiment, then on the visiting committee, then on the board of governors for a while. Herman Grunder was director at the time, at least in part. And I've, of course, maintained various connections institutionally, as Peter has recounted since. What I want to talk about today is urban science or urban informatics, something that I've been pursuing for the last 5 years in the context of starting this center at New York University. Urban data is a thing that is happening. There is certainly very much an analogous, I like to think of sister effort here in the urban CCD effort that Charlie Catlett and others are involved with. And we're now seeing this spring up at cities and universities really around the world. And why is this important? For me, cities are where society happens. Half of the world's people live in cities right now, and that number will grow to 70 some odd % by the middle of the century. There's some sense of the evolution in different parts of the world. Cities are where the people are. It's where the economy happens. It's where innovation happens. It's where sustainability is going to happen. The interesting thing about cities is that our understanding of them, even though they are the probably most complicated manifestation of humanity on the planet, interacting systems of systems that deliver security, shelter, mobility, etc. to people, our understanding of them up until recently has been pretty anecdotal and episodic. And it is the deluge of data that we're now seeing throughout society that starts to make this a very interesting subject. And so just about 5 years ago, when I got out of the Department of Energy, I started to think about what does it mean to instrument a city as a scientist would. And I realized we want to know about the physical infrastructure of the city, the roads, the electrical grid. We want to know about the environment, noise, pollution, meteorology, and we want to know about the people. This perhaps makes cities very different than other systems we might study because there are immediately issues of privacy and security, but nevertheless, if we're going to study cities, we have to study the people in some way. And if you could really instrument a city, there are many organizations and entities who will be interested. The government, obviously, to be more efficient and better serve the people themselves, and all manner of entities in the private sector who have interests in the city, whether it's retail or insurance or political campaigns. They all want to know what's going on in cities. And what, of course, makes this interesting now is that there is a lot of data out there. The city itself generates lots of data through its records, whether it's administrative records or operational records. Modern social media generates lots of data about cities. We have sensors everywhere in our pockets, increasingly in portals for people, in vehicles, in buildings. And there's the opportunity to do novel sensor technology, some of which I'll show you in the next 40 minutes or so. And so the challenge here, I think, is threefold for those of us who are researchers. One is, can we develop the technologies and methodologies that make sense of this massive amount of heterogeneous data? The second is, what science can we do with it, either by looking at patterns within a city or comparing one city with another? And then the third, which is perhaps where the greatest societal interest is how can we apply that understanding to make cities better, either existing cities such as Chicago, New York, or newly built cities as are going up in Asia at an astounding rate. So I first got into this, as I said, just about 5 years ago. In April of 2012, CUSP, the center that I've been leading, is part of an effort by Bloomberg, then Mayor Bloomberg, to bring tech to New York City. And we were the second winner of a competition. The first winner was Cornell and Technion, and they are building a nice campus of a research university on Roosevelt Island, a much grander effort than what is envisioned or has been for us. We were announced about 4 months later. And at the time, I had no idea what we were doing. And so all the big shots were talking mostly about the real estate involved in the deal. I was in the back. We were trying to figure out what we were going to do. 4.5 years later, we've got some sense of what this field is about, at least from our perspective. And so what I want to do is take you through some of the examples, probably open your minds a bit to thinking about cities, applications, and science, and maybe stimulate some interesting thoughts on your part. In terms of the research, we are both a research and education operation. I'll talk a little bit about the education toward the end. But the research, having grown up around the DOE system, I realized that it was going to be facilities that would anchor an institution, much as they anchor the national laboratories. And so we conceived of 3 facilities, which I will tell you about a bit about each of them. The themes and the research groups that have evolved are building informatics, information about the buildings in the city. Can we learn about their operation and construction and, of course, help improve that? Mobility is an obvious theme. Sound is something that we thought about early on, and I'll say something about progress in that. And then urban energy more generally is something that has emerged as a theme. And within those themes, there are a host of projects that get executed, many of them by the students, that impact directly on city operations or citizen concerns. And so I'm going to take you through a potpourri of a number of these and give you a sense of what we're doing and what the potential is. The first thing to realize is that the city generates a lot of data. This is a now 3-year-old figure that Bloomberg's administration put together. Bloomberg, of course, is a very data-driven guy. And the first thing he did was to mandate that all of the data that the city has, whether confidential or not, be at least aggregated in one place. He established the Mayor's Office of Data Analytics, which takes feeds from the Department of Transportation, city planning, finance, sanitation, and you can go around. So at least all of the data is now in one place. And increasingly, I'm understanding that when a city agency now wants some data, let's say from the police, they go to the agency that manages this data store rather than directly to the police agency, let's say. Of course, some of this data is pretty closely held, others not. We have access to all of this, the open data, obviously, but also the closed data on a project-by-project basis. So we spend a lot of time with lawyers negotiating data sharing agreements. Second, there's an awful lot of federal data out there. This is an example of some census data. It shows the Gini index, which is a measure of income inequality over the city. And apart from the actual data itself, what you should be impressed by is the granularity that this data is available at. Just how finely resolved we can get measures, in this case, of income inequality. There's also all kinds of social media out, tweet feeds. Some fraction of them are geolocated with confidence. You can infer geolocation from about another 40%. And so this is just a map of where people are tweeting from over, I don't know, I think it's a year or something like that. So. The facility that we built, or building still, to handle all of this is being built by Julia Lane, who has deep connections with Chicago in a research sense. Julia is a labor economist, but over her career has built a number of data facilities. The criteria are that the data be clean, that they be interoperable. There are 4 ways of specifying a building in New York City. For example, there's lat long, there's street address, there's something called borough block and lot, which is the tax ID, and there's something called the BIN or building identification number. You need to map one to the other, obviously. Data need to be clean, interoperable, and multi-layer security, and then provide the tools to be able to analyze that data if you're not an expert. We are building this up now. It's on the web for collaborators. You can get an account and start to browse and see what's up there. Okay. So first facility, someplace where we can keep the data. Second facility was conceived of in analogy with neuroscience, where if you want to understand how the cortex works, you would take a square centimeter of cortex and instrument the heck out of every neuron there in order to understand how the broader brain might work. We thought an intensive instrumentation of a community, nominally about 10,000 people, would be an interesting thing to do to really understand how mobility, environment, economics, communication, resource flows take place in great detail. That goes under the umbrella of Quantified Community. This is being led by Professor Constantine Contacosta at CUSP, and it takes the form of various instances. It started out as instrumenting one building in New York City, the Time Warner Center. It has expanded to instrumenting Hudson Yards, which is a large real estate development going up on the west side of Midtown Manhattan, instrumenting a section of lower Manhattan with Wi-Fi access, trash cans, street-level cameras, noise pollution, and so on. More recently, Red Hook, and now expanding to several different neighborhoods in the 5 boroughs of New York in what's called Neighborhood Innovation Labs. What do you get out? Well, here's an example. Red Hook, a number of Wi-Fi access points to which we have data on who's connecting. If you walk by with your Wi-Fi enabled device turned on, it logs your MAC address, even though you may not intentionally do anything with it. And so you can get a graph, as shown on the right, of the number of first-time connections over a year and get some sense of population traffic. You can do better by realizing that over a year, you see some devices every day, but you might only see them during working hours. You see other devices only once, and you might infer from them that they're tourists. And if you see them outside of working hours regularly, you might infer that they're residents. And so you can get, in this case, with hourly resolution over a week, separation of the population of residents, of workers, and of casual tourists, let's say. And you see here in this span over about a week, by the way, this is July 4th, and you can see that that Monday is depressed relative to others. You see a phenomenon that we will see over and over again, urban physiology or urban pulse of the city. The city happens every day. Understanding that regularity and understand the anomalies relative to that regularity is an important part of the science that one wants to do here. Building energy efficiency, you can get right out of records data. This is a histogram of the energy use intensity for about 1,100 office buildings in New York City. New York City passed a law some number of years ago that mandates that every large building above 50,000 square feet has to annually report its energy use, electricity, natural gas, heating oil, steam. And so we can, Constantine in this case, can make a histogram of the energy use intensity, BTUs per square foot per year for these buildings. And you can see there's quite a bit of variation, factors of 3 or so over the buildings. Is that due to building construction, building operation, the kinds of activities in the building, or is it due to just plain old misreporting? You can do the same thing for residential buildings. It's a more regular distribution, but there are still factors of a few in the energy use per square foot over the buildings. You can try to understand that. Here's one cut at the data. This is the energy use intensity as a function of the year in which the building was built. This should be 1890s, for example. If you just focus in on the offices, you can see that the new buildings use much more energy per square foot than the old buildings, having to do in part to the glass curtain walls that are terribly energy inefficient in the new buildings. So you can do cuts on the data like this. Give you a different sense of the data available, the Taxi and Limousine Commission in New York City mandated that every taxi ride shall be logged starting in 2009. And so for each of the 180 million rides a year that happen, one has time, start time, end time, location, start and end, driver, medallion, fare, and so on. And lots of interesting questions can be asked. One simple cut again at the data is just to plot the number of trips per day over a year, or in this case 2 years. Again, you see a regular pulse of the city, but anomalies, in this case due to Hurricane Irene, here Superstorm Sandy. You can see here a marathon that was run in the city, clearly Christmas, Thanksgiving, and so on. So you see these perturbations in the life of the city. You can look even in more detail. One of the computer science challenges is to simply be able to browse through 1 billion records in a time that the researcher can find useful. Here I show you 1 week in May, trips that start from the train stations and the airports, and the number of trips at 15-minute intervals over a week, and the number of tips at 15-minute intervals over a week. You can see again, hour by hour or minute by minute repetition of the pattern having to do with when trains or planes arrive. And again, you can look for anomalies relative to these norms. Let me shift into some imagery. One of the things in all cities, I'm sure in Chicago as well, traffic accidents, collisions at intersections or with pedestrians. Can you get some handle on that? And one of our faculty, who's a transportation guy, Khan Osbey, noted that you can't always catch an accident as it happens. They happen too rarely, but you can catch near misses. And you can try to understand the statistics of near misses. For example, the time to collision, if the trajectories had continued, how long would it take until they actually collided? Or the time how much did you get a near miss in this encroachment in spaces? And so what we did was to set up a video camera. Let's see if this video is working. No, that isn't video, sorry. Watching an intersection outside of our offices. This is one of the busy intersections. You can track every vehicle with some automatic image recognition and then do experiments to see how close, or data analysis to see how close they come, and pick up the statistics of near misses and understand what might be driving them and how you might be able to mitigate them. Okay. Moving on to an environmental issue. When I came back to New York City, I grew up in New York, left at age 16, and didn't come back until 5 years ago as a resident. And it was a wonderful city to come back to, much more vibrant than when I had left it. On the other hand, my biggest complaint was noise. And I swore I was going to get the guy who was banging the trash cans at 3 in the morning. And so 3 years ago, we started with 2 postdocs, a noise project to build what has evolved into a system of sensors and reporting to detect and identify noise violations. So what they did, is to build a box which contains a custom MEMS microphone, which is accurate to plus or minus 2 dB. One of the postdocs in the faculty involved are acousticians, and so they care a lot about the precision of the measurement. You need 2 dB in order to do noise code enforcement. The boxes exfiltrate data through the local Wi-Fi. They take that power from the mains where they're installed. They have a small processing element. And most importantly, they do machine listening in the box so that you don't send back the raw audio, but you just send back feature extraction. There's a picture of one of the boxes deployed. It's on a ledge above street level in lower Manhattan. You see the windsock protecting the microphone, and you see the pigeon spikes that keep the pigeons off the box. Real world stuff, right? Right now, we've got 17 of them deployed. When this slide was made, it was 10. We're now up to 17. We'll have 100 by year's end. The boxes cost, I think this chart says $100 a box. We're down to $85 a box now. They've been taking sound pressure level data already, but they're taking real audio also to train up the machine listening algorithm. Machine listening has been trained so far on soundscapes that you can get off the web, but we really need the real soundscape in order to do the training well, and we've got real-time telemetry coming back. So this is just a little demo of the machine listening. Let's see if it works properly. So there's the car horn, it picks up the car horn. Really. Et cetera, right? Why is this useful? Two reasons, or maybe three. One is data compression. Second, you don't want somebody having to sit and listen to God knows how many thousands of audio streams. And the last is a legal issue. Legally, you may not record sound like this on the street. It's a remnant of the wiretapping laws. Curiously, you can do video, but you may not do audio. And by doing the processing in the box, we feel as though the lawyers tell us we're okay with the legal. Okay. Privacy is a big deal, as Charlie and the Array of Things know really well. Actually, this project was just in the local news. Evening news. It's been in the New York Times in the last couple of weeks. So we think we're managing the public perception issues pretty well at this point. All right, let me turn to imagery, which is something that I think physical scientists probably have a natural inclination toward. Certainly, I've got an inclination toward this as well. The story for me actually started when Bob Rosner, I was here in January of 2012, Bob and his wife and my wife, we had dinner, and then he took me up to the top of the one of the towers, and we looked out at the lights at 11:30 at night in Chicago. It was a cold, clear night. And having grown up at Caltech, I looked out and had been thinking about cities, and I said, aha, astronomy, all right? Because there are lots of lights out there. They have different colors. They go on and off, but they don't move. So felt like astronomy to me. And I started to think about what you could learn by watching a city from an urban vantage point. A little bit later on, probably a couple weeks, I found this image in the National Geographic, which I think illustrates the point nicely. This is an infrared image. I did not take it, but we have similar images. So we're looking at the heat. And what's interesting is, for example, that building, you can read the thermostat setting in every one of the apartments. Some are hot and some are cold. That building, we know, has got a data center in it. And so it's hot on the bottom and it's hot on the top where the vents are. And so we have correlative data that we can bring to bear in interpreting the images. And then that set of buildings turns out to be a public housing project. And in typical New York City fashion, the heat's turned up full blast and people have the windows open to keep the apartments. And so you start to think about this for a minute. This is a single sensor, right? One infrared imager. It's synoptic in the sense that I can cover 1,000 or more buildings with one sensor. It's non-permissive. I don't need anybody's permission to go put in a smart meter or a thermostat and so on in every apartment. It's persistent. So it's not like a flyover where I might get the data once and then have to wait at least a day if it's a satellite or more if it's an aircraft. I can take images at pretty high cadence. And then it's got high granularity because the modern sensors let you see individual windows, for example. And it's not expensive. So I thought that would be fun. We started doing this. And it has since evolved into really a set of proofs of principle of what you can imagine learning with a host of different imaging sensors, ordinary optical, thermal infrared, short-wave hyperspectral, and then long-wave hyperspectral. And I'll show you a little bit of some of the kinds of things you can do with each of those. I'll start off with the view. This is the view from our, oops, let's go back. Oh, I see, no, okay, we're good. That's the view from our offices. Unfortunately, we're going to be moving out in about, at the end of July. We won't have as grand a view, but those of you who've been there, we see a lot of the city. The Empire State Building, to give you a sense of scale, is visible. Here, it's due north of us and is 3.8 miles away. So you can get, this image was taken with a 1-inch lens or something like that, so it's not. We have a LiDAR topography data set of the city. About 5 years ago, there was a LiDAR overflight that shot 15 billion LiDAR points, and so we know the topography of the city, or as it was at that time, it's changed a little bit, but we know the topography of the city with 1 foot vertical and horizontal resolution. And so you can fuse the image with the topography. It's a simple exercise in geometry. We had an undergraduate from Yale do it a couple summers ago. And so, for example, you can just sort all the buildings by distance. That's not such a great feat. But more importantly, you can identify every building that you see in the scene and then plot them on this map, in this case of Manhattan. There are about 1,000 buildings there. And interestingly, once you have identified the building, the city has a tremendous amount of data about each building. It's in a database called Pluto, the Public Land Use Tax Output, which tells you about economic value, volume, occupancy, energy use, et cetera, et cetera. So we know what we're looking at. And so you can then fuse it with other data. In this case, this is a color code of the large buildings in the scene by energy use intensity. And the red building, for example, over here, the hot buildings, so to speak, turn out to be hospitals and broadcast studios, which run, it's not surprising. But also we're able to outline in black here every building that is heated by heating oil as opposed to natural gas. And heating oil turns out to be a big pollutant in the city, so you would like to know that. So this is a demonstration of the fusion of 1, 2, 3, 4 data sets together in an image to let us understand what we're looking at. Okay, this is a 1 night's worth of optical imagery taken now about 3 or 4 years ago. 1 frame every 10 seconds going through the night. You can see the lights in the foreground where it's residential go on and off. The commercial buildings mostly in the back, pretty steady. The Empire State Building went off already. Chrysler Building stays on all the time. Daytime comes, you see the shadows moving across the city. You'll see clouds moving across the city. Interesting if you're interested in insulation for heating or for rooftop solar and so on. So what can you learn from this? We started, Greg Dobler, who is an astronomer, is one of the CUSP researchers, started saying, let's isolate the sources and just understand the dynamics. Greg pulled out 4,000 windows by hand, and this just started to make the light curves for each window. This is 1 window over 1 night. I have no idea which window it is or which time it is, it doesn't matter. And we just show the intensity, and you can make up a story. At 7 p.m., somebody came home and turned on a light. At 9 o'clock, they turned off some of the lights, sat down to watch TV. At 11:30, big drop in the lights, end of the news, or gone to bed, and then either the baby woke up or there was insomnia or something like that, right? So you can make these light curves. You can identify the transitions in them. For each night, we identify what's called a big off, which is when it looks like they went to bed, and a corresponding big on, which is the biggest on transition. And then you can plot for these 4,000 windows the ons and offs over 3 weeks, see the pattern, look for anomalies. One of the amusing things you can do that starts to bear on behavior, you can take all the lights for Monday and order them simply according to when it looks like they turned off for the night. And you get this pattern, which is, of course, the cumulative of one of these distributions. Then you can look at the Tuesday data, but sort the lights according to the Monday ordering. And you can see that there is some memory, but not a great deal. There's about a 1 or 2 hour decorrelation from night to night as to when these lights go off. Of course, there's some small subpopulation, about 6%, that go off at the same time every night. Those are the lights that are on timers, and we can find those. And then, but if you do the Tuesday data with the natural Tuesday ordering, you can see you come back very much to the same distribution. So people in aggregate are pretty predictable, but the individual behavior is rather random. Pretty interesting, we thought. All right, what can you learn during the daytime? This is a raw image over about 3 minutes taken during the day. And it's hard to see anything going on except the traffic moving without some cue. And so what we did was to background subtract the image, as shown on the bottom. And you can see these big blobs that emerge. And we have colored in the blobs over here. There they are coming out. And what is that? Well, it's that. Okay, the boilers that run by heating oil, when they fire up, emit this big black cloud of stuff. Okay? Needless to say, the environmental folks would like to know who's doing that, when is it happening, where is it going, and how can we try to put a stop to it. And so we've got a pretty good way now of watching 1,000 buildings at once and getting a sense about this phenomena. You can do other things with it. Of course, you can get some measure of the winds by natural tracers. You could trigger observations of spectroscopy to look at the composition of the plumes and understand about the adulteration of the heating oil, which is another issue in New York City. Okay, different, more imaging, but this is just tremendous fun. You can do hyperspectral imaging. You can buy a hyperspectral scanner for about $80,000. We did acquire one. For those of you who are not physical scientists, your ordinary camera takes a picture in 3 colors, red, green, and blue, and there's a red, green, blue value for every pixel in the image. A hyperspectral camera takes a picture in about 1,000 colors at once, and so there's a whole spectrum for every pixel in the image. And from the pattern of the spectrum, you can identify, among other things, lighting technologies. And so here I show spectra for different lighting technologies. Here's high-pressure sodium and LED, fluorescent metal halide, and different brands of LEDs. And then here's a picture of the city in which we have identified, at least for the bright sources, the different lighting technologies. Again, non-invasive, broad coverage, granular. If you're interested in selling high-efficient light bulbs, or you want to measure the rebound effect, where people are thought to use lighting more when they get a more efficient light bulb, you can study that using this kind of measurement. You can see here's a close-up of the Manhattan Bridge. It's got different technologies on the roadway versus the necklace and so on. And of course, we've gone out and verified with the city that that is in fact the case. All right. Different one, again, imaging, some insight perhaps into the electrical grid, what you can do. Almost every lighting source in the city that you see is flickering at 120 hertz. If you think about an ordinary incandescent bulb or the old-fashioned fluorescents, they're driven with the line frequency or twice the line frequency. And you might be interested in both the frequency, but more importantly, the phase of those sources, which are a measure of the load that is on the grid, transformer health, and so on. And so we did an experiment in which you can take an ordinary camera and put a liquid crystal shutter in front of it, drive it at almost the line frequency, and look for the beats in the image to measure the oscillations of each individual source. And here we focused in on that source. It's a little bit hard to see, but it is there. There's a close-up of it over a couple minutes. Typical astronomical sort of image, kind of grainy. But if you do the usual astronomical analysis, you can isolate the oscillations of it and then do a frequency analysis to get the frequency, which comes out at about the right frequency. But more importantly, you can get the phase relative to a fiducial in the scene. And so you can infer the wiring topology of the city. You can infer what generating sources have turned on and off, and so on. This is in a paper that was just presented last week at a conference out in Stanford. Other things you can do, more imagery. We're now back in thermal IR. These are two images of the west side of Manhattan taken from Hoboken. In the thermal infrared, 2 minutes apart, maybe 3 minutes apart. And the difference image is shown on the bottom. What do you see? Well, we see some hot plumes coming out of buildings, so they're burning natural gas or oil, whatever. And then we got real interested in that feature over there. You see it's here in this image. It's not there in that image. What happened? Well, as I said, we had building ID. And so we identified that as that building, which is next to the Google building in Manhattan, if you know. It's on the West Side Highway at about 16th Street. And what was interesting for us is that row of cooling towers up on top. So we're really quite sure that we caught one of those cooling towers turn on. And so what I've now got is a way, if I'm at the right vantage point, of watching the HVAC system of many buildings at once continuously to get a sense of how this building is generating heat, releasing heat, and so on. You can do something else. Here's the image again, or similar image. Because you have multiple wavelengths, you can do what's called a temperature emissivity separation and separate out the material properties of the surface that you're looking at from its temperature. And so you can make this kind of map, which is a map of the temperature of the surfaces that you observe. Clearly, if you're interested in the urban heat island, if you're interested in interbuilding radiation coupling, if you're interested in the heat coming off of the city, this is a really interesting way of generating data to calibrate models for what's going on. One more, and I think this is the last set of data, almost the last set of data I have. One of the images we borrowed from the Aerospace Corporation was a long-wave hyperspectral imager, 7 to 13 microns, 128 spectral channels. It was built for and is owned by the Air Force, and they use it for detecting plumes, chemical plumes in jungles where people are doing things they maybe shouldn't be doing. And one of the things I thought about early on is let's go take one of these things and turn it on the city and just watch. And so we did. This is, again, the west side of Manhattan. And one of the things that we found chemically was a surprise is there's a lot of Freon-22 coming out of the city. The instrument is extraordinarily sensitive. It can see a spray can of stuff at 5 miles. And we see this whole haze of Freon-22. This is a chemical that is an ozone eater. It is illegal to buy or manufacture this chemical in the US, but if you have a legacy stock or you have a legacy refrigeration equipment, you can use it up over the next 5 years or something like that. So again, we can pinpoint all of the Freon sources in the city. That's sort of interesting. We see ammonia too. There's a lot of ammonia coming out. We think that's also from refrigerants. And then there's this one which is amusing, and I think this is actually the last data bit I've got to show you. As we were watching the west side of Manhattan, we saw in the various chemical maps, we saw a lot of acetone coming out from that particular site. This is about 3 or 4 hours over an afternoon on April 7th, about 1.5 years ago. And acetone, okay, we're thinking, what's that? I thought immediately nail salon, but it turns out it's more than that. So again, we have buildings ID. We identified it as 677 Washington Street in Manhattan. Turns out it's 679 Washington Street. There's a cleaning establishment, dry cleaners, that has on-site dry cleaning. And so we're seeing the acetone that these folks are venting. It's legal. Still interesting. We get a proxy for their economic activity. But if you remember the TV show Breaking Bad, if you're doing things, making drugs, you're using volatile organic solvents, and if you're not careful with it, you will leak. And so we're trying to get the police interested in using this to queue. The west side of Manhattan was not the right place to be looking for drug labs. The instrument itself, just a word on the technical, the instrument itself, if we were to reproduce the instrument, it's cooled by liquid helium and is about a $3 million instrument. Aerospace believes that they can put a cryocooler in to make it much more compact, thermoelectrically cooled, and it's about $1 million and something bucks. So we've got a proposal into NSF to buy one and start pointing it around the city. We could only rent this. Okay, good. I'm going to skip through this because we're running short of time. Let me just say a couple words about education and then wrap up. Part of the deal with the city was that we would start educating people in what we were doing. We run a one-year master's program in applied urban science and informatics. We're now on our 4th cohort. The curriculum has become better defined. The students do about 30% of informatics, databases, visualization, modeling. Another 30% in urban. What are the problems in cities? How do cities work? How do city governments work? And then about 40% in a project that they execute over about 5 months, usually in collaboration with a city agency, a 5-student team or so that brings together diverse skills to do something that the city thinks would be useful. That was the first class, which graduated in 2014. We are now, so there were 23 students. The next class, we had 64. The third class, I'll say something about the city employees in a moment. The third class was 82, and the current class is about 85. Interestingly, for each of these last few classes, we've had people who are New York City employees and are doing the program half-time, so it takes them 2 years. These are really interesting students to have. They have real-world experience in the city government, so they bring a perspective to the classroom that the other students find really interesting. And they take the skills back with them when they go back to the city agencies. And we also have friends when they go back to the city agencies, because one of the most difficult things is to get the data out of the city. So it's good to have friends. Here are some of the projects. Last year, we did 15 projects for the city. Commercial development analysis, consumer fraud detection, illegal dumping, condition of parks, and so on. The students just love this, and the city seems pretty interested and engaged as well. Work for a lot of different agencies, not only the city agencies, but also the Attorney General in the state, and some of the broader regional agencies. Where do the students go? We're finding that they get placed in city governments, they get placed in NGOs, they get placed in startups or big companies that are interested in serving the city. The background is really interesting of the students. We've got everybody from physical scientists, computer scientists, civil engineers, urban planners, economists, even a psychologist or two. And it's really interesting to bring them all together. They're all quantitatively talented. The GRE scores are as good as any engineering program in the country, but they're all interested in cities. And so it's great fun, not only to teach in the formal classroom, but to bring these teams together and get them to work on real problems. I see I'm running out of time. I've got some other points that would be fun to talk about in the practicalities of doing this, but let me stop at this point. Thank you for your attention. We can talk about some of these during the Q&A and just open it up for questions. Thanks.
Thank you very much, Steve. I think that's probably provoked a few questions, thoughts from the audience, so let's open it up.
Thank you very much. This was really interesting, actually, presentation. I have a question about the social media as a source of information. You mentioned in a couple of the slides at the very beginning that social media information was also used. And in the light of the claims that we live in a post-factual society, how does the science use that information?
That's a really interesting question, and maybe a bit too topical for me to give a straightforward answer. Some of it is just the externals, okay? What's the volume of tweets, what's the rate of tweets, the location of the tweets, maybe some demographics. That's already got a lot of interesting information in it. If you want to get into the content, then you start to get some of the issues you raised. I've got no good answer other than to say it's an ongoing topic of research. One of the researchers we have is a guy named Dan Neal, who's from Carnegie Mellon. He's done a lot of work on epidemiology, crime, and so on, using some of the social media feeds. I think some of it here in Chicago, actually, as well. Charlie? Oh, Peter, yeah.
The city of Chicago watches tweets for events. And recently there was a backpack that was hung in a strange place in Millennium Park. And the police got the tweets 8 minutes before the 911 call. So it's a sort of early warning system if you're watching it properly. I'm sure New York is doing the same thing.
Yeah, I'm very curious about your third bullet point here, in that based on your experience, it makes sense that your city governments will be your first customers. But I would like to get a sense of what you think is going to happen in the next 5 and 10 years, and that will you see an evolution where we're going to expand the customer base, people interested in funding your work, from city governments to companies and industries, and just get a sense of what industries do you think would be very interested?
Yeah. We started off thinking that there was great commercial potential here, and that may still be true, but so city governments as customers, not great. Procurement laws, less than agile bureaucracies, and they're strapped for cash. R&D for a city agency is really unusual. Right? They're much more inclined to go buy something from somebody. Firms, I think there is money to be made in providing data to commercial entities. If you're an insurance company, you want this kind of data, building operators, and so on. And clearly, you know, the profusion of apps and all kinds of information pushed out to citizens is another clear market. I'm going to annoy my city partners now, but I'll say it anyway. If you can do things like this synoptic imaging, which does not rely on city infrastructure at all, I don't need the city's permission, I don't need their light posts or whatever, you're much better off than if you have to go through a municipal entity. In terms of the funding for research, I think the federal government, as a result of at least the current federal government, the result of a PCAST exercise that Charlie and I were involved with, has raised the profile of urban technologies. NSF is putting some money into that, or repackaging some money into that. But it is not a recognized either academic field yet or viable field of engineering, but it's getting better. The Metro Lab Network, which is a network of 35 different universities and cities around the country, their partner cities, New York, Chicago, LA, South Bend, Indiana, is a kind of a forum for urging the federal government to think about cities as an R&D venue. And we're starting to get a little bit of traction, I think.
I'm going to ask a question first. So you presented this very much as astronomy.
Yeah.
You're sort of looking out there, right? Occasionally there are natural experiments happen, a supernova, something like that. How about, you know, what I would call a real experiment? You know, short of my going out to Millennium Park and putting something on a pole. Have you thought about that? Do you do experiments? How would that work?
Quantified community, well, I mean, we haven't done yet, but the quantified community is meant to be a test bed also where you might be able to put, one of the things about experiments is you run into the IRB issue, right? Even for taking the pictures, we went to the IRB and we said, we're going to do this. And they said, why are you bothering us? Everybody looks at everybody else's window anyway in New York. But we keep the resolution low enough so that you can't see anything. There was a quote that has come across my horizon recently due to Feynman, when he was talking about biology, and I can't remember what vintage this was. And he said, these are really complicated systems, but the way that you understand it is just to look at the thing. And I think we're at that step. Biology is well beyond that now, but I think we're at that stage now for cities. We're just trying to get a sense of the phenomenology that these new data sources enable.
As a lawyer who has a very strong interest in analytics and sensors, I found your presentation incredibly interesting and deeply, deeply disturbing. So I do have a few questions. One of them is, first of all, have you considered what the desirability of transparency for the citizenry as you're talking about using municipal or other government sources of data so that they understand exactly what their tax dollars are being spent on? Second, have you considered some of the trade-offs? Because, for example, you can get data from, presumably from Uber or Lyft that would probably be much more granular than requiring taxis or doing the much more crude analytics from the taxi data. So there are trade-offs between licensing versus developing your own. Yep. And finally, I guess the general question that I would have is, these experiments have been focused on New York. I'm wondering whether you've come to the conclusion that different cities have different kind of fingerprints that might suggest something about differences between the peoples who live in the various cities. So apologies for the multi-part question, but it's extremely interesting.
Let me say first, we are an academic institution, and we don't do anything that we firmly want to keep from the public. There have been news stories about the imagery work, about the sound, as I mentioned just in the last couple of weeks. And so we're out there. As long as we are addressing problems that people care about, I think people are willing to understand that this is going on. Can you do more intrusive or invasive things? Sure. We have a data ethics training for all the researchers and the students. It's a manual, policies. We log access to all the files in this data facility. Some files, as I mentioned, are restricted and you need to be signed off on and so on, so we worry about that. We sponsored a book a couple years ago on privacy in this era of big data, and that book is available. It's chapters by lawyers even, data scientists, ethicists, and so on. So we're paying attention to it a lot. I have to say we are much more careful about it than some of the data companies, because they have no need for transparency as to what goes on behind the walls. Okay. In terms of data access, my second data bullet, everybody hoards the data. I like to say it's the second most basic human urge, is to hoard data. The researchers do it because it's priority in publication. The commercial firms do it because it's valuable. And the government does it, the government agencies do it because it's government turf, or it can be embarrassing if you shows how poor your performance is and so on. So breaching these stovepipes of data is a major and frankly unexpected chore that we deal with. We spend, you'll excuse me, unfortunately, a lot of time with lawyers trying to get the data agreements sorted out. But once you've done it once or twice with an agency, it gets easier as they start to trust you. Okay.
Thanks very much for a fascinating talk. I believe you said some of the data sets are open. And I wonder if there's been any interesting or novel work come from unexpected places from that. And the one example I remember reading about was a guy who analyzed the most ticketed parking spots in a city. The worst places to park.
So there is an open data movement that's been going on for now a couple years, maybe more, at the federal level, but also at the city level. If you go to opendata.nyc.gov, there are 1,500 data sets up there. In most cases, it's just the agency dumping raw, uncleaned, uncurated data out, but there, and I'm sure Chicago's got the same, but there's a whole community of, let me say, amateurs, some very talented, who are exploiting that data to do interesting things like the parking tickets and so on.
So there's a sort of a train spotting community which is developing around this. I can consider. I think actually that we could go on for a while. This is really exciting, very interesting. I think you're seeing the beginning of a new field of science. I'm not quite sure what it's going to look like. It's really impressive what you're doing, and I'm glad we're sort of teaming up.
Yeah.
So thank you again, Steve.
Okay, very good. Thank you.